So you forgot your suit, Denis?
I hesitated, but then it's better casual.
Okay, you are in computer science, so that's the norm.
So you will all have your...
Sorry, yes, I can hear you, but not very well.
Will you have all your slides with you in that slide? That's cool.
Oh yes, so everything will be. But if you want to see, so a small sneak peek of what I can do. Not very well.
Cool.
So I can do this and full screen slides.
Yeah.
Denis, can you hear me?
Yes, I can.
Because I think there is some echo because I'm also logged in into the YouTube channel.
There is no echo when you talk. But
Do you hear me?
Yes, I can. Ah yes, so now I hear what is happening on your YouTube stream.
Logged in into the YouTube channel.
There is no echo when you talk.
Huh? No, I had the impression that when I talked, okay, when Bram was talking.
So now I hear what is happening on your YouTube stream.
Yeah. Into the YouTube channel.
There is no echo when you talk. Okay, so I have put your sound back on YouTube so that people watching the live stream can follow you. But that's nice then to know that everything is working, even though it leads to a weird echo. So yes, for the people watching on YouTube, there is about 30 seconds of delay, maybe, so quite a long delay. So when we will ask questions at the end of the defense, it may be a little bit awkward. So it's not that I don't see your question, it's that there is a very long time between the moment I answer the question and you see the answer of the question.
Okay.
Hello?
Hello.
Hi.
Hello.
Everything ready?
Yeah, there are a bit problems joining.
I see now that Bernard sent an email as well for the deliberation.
Yeah.
Yeah, thanks. So
Okay.
that looks
now
nice.
That one is around because both Manuela and Robert will not attend, but both have sent me questions.
Mm-hmm.
Okay.
And then I have been informed by Elisa that that we should have a separate link for the deliberation. And I have sent an email to you like 15 minutes ago. So I have seen that Bram accepted that invitation already.
Yeah, but I have also seen the link, yes.
Yeah. So then once we have the deliberation, we will use that link.
So then it's Bram and me and you guys, basically.
Yeah.
Okay. Let me see.
And then Denise, I have one question for you. Your bois, how do you pronounce that?
Bosch, like in German.
Okay.
But Bernard, I'm not going to correct you today. It's just that the other time you hesitated so long.
Yeah.
Like you said, Elisa Gonzalez, that I said it to help you. It was not meant impolite, sorry.
No, it's not for that reason. I also asked Denis how his name was pronounced.
Okay.
And the audience on which channel are they, Denis?
So they are now live on YouTube. So the link that was in the PDF announcement. So currently there are 30 people watching us. Well, not really watching, because so for the members of the jury, no one on YouTube sees you. So it was too difficult on a technical point of view to make that. But everyone can hear what we say.
Ah, okay.
Yeah.
That's interesting information. Thank you for letting us know.
Yeah, and also because in the beginning I was both on YouTube and on the Teams meeting, but there is a delay of 30 seconds with the YouTube. Then it really gets weird. So don't try to also follow on YouTube or you will mess up everything.
So we have 30 seconds, Bernard, to interrupt the YouTube streaming if you stop, which is not acceptable.
No, but I was talking to Denis and then I heard myself talking to Denis 30 seconds again later. But at least now we are aware of the problem. That's not really a problem.
Yeah, voilà.
Yeah. So we can start at 5 sharp, Denis?
Oh, yes, if you want, yeah.
Yeah. Then when it's time, I'll start with it.
Bernard, will you start first with the external examiner's questions?
Yeah. So I follow the normal procedure, and even if they are not present, we will start with their questions.
Okay.
So we are already 5 o'clock. Welcome, everyone. So today we are here together for the public defense of Denis Stechelmacher. The title of his thesis is Reinforcement Learning for Real-World Robots. And the supervisor of the thesis is Professor Anne Noé of the Artificial Intelligence Lab of the VUB. I'm the head of the exam commission. My name is Bernard Manderik. I'm also from the AI lab, and I'll be assisted by Professor Elisa Gonzalez Boix from the software engineering research group, also at the VUB. Then we have a number of external thesis committee members. And the first one is also from the VUB, but from the Faculty of Engineering, Professor Bram Verborgt. He's in the robotics research area. And apart from that, we have 2 people from outside Belgium. There is Professor Babushka from the Technical University of Delft, also in the robotics field, and Professor Manuela Veloso at Carnegie Mellon University, but at the moment she's on leave and heading the AI lab of JP Morgan. So these were the thesis committee members, and the rest of the rest of the evening will be organized as follows. So first we will have a presentation by Mr. Stechelmacher. It's 45 minutes. And after that, we will have a number of questions. First of the thesis committee. And since this is a public defense, also the public can ask some questions. After the presentation of Mr. Stechelmacher, we'll discuss how we will organize questions from the public. Okay, so this is what I had to say. Now I give the floor to Mr. Dennis Steckelmacher to give his presentation.
Thank you. So I'm just starting to measure my time. So thank you for everyone joining my presentation. So the 4 committee members joining, unfortunately 2 were not able to join, and also the 21 people watching this defense live on YouTube. So I'm very pleased that you find my research interesting. So now I will present my research that is about reinforcement learning, sample efficient reinforcement learning algorithms applied to the real world, with an illustration in this presentation on a motorized wheelchair. Okay. So sometimes I have to struggle a little bit with the technicalities, but now it should be working very well. So this presentation will basically be split in 3 parts. So I will first give a gentle introduction to reinforcement learning. So I know that most of the people watching us are not from an AI background, but are interested. And so I hope that this part of the presentation will help understand and position then the contributions that I will present later. Then I will present the result of my 4 years of research at the AI lab in Brussels. And then I will present the application of that on a motorized wheelchair. So even though it's a motorized wheelchair, so it seems quite specific, it's just an example of what we can do with the algorithms that I will present as my contributions. So first, it's interesting to position reinforcement learning in the scope of artificial intelligence and computer science. So artificial intelligence is quite a broad area. So for instance, GPS, navigation, planning, scheduling, production machines, and things like that, all that is part of artificial intelligence. Even though nowadays what we usually think about when we say artificial intelligence is machine learning, that is a class of algorithms that allow, a program to learn something. So it will learn from data, for instance, it will acquire knowledge, and then the goal is to be able to use that knowledge. And reinforcement learning is a subfield of machine learning that allows a program to learn how to do something. So what we consider in reinforcement learning is that we have an agent, and so the agent is the program that learns. And then we have an environment. And so the environment is what is the agent interacting with. So the agent will execute a succession of actions in the environment. So for instance, make motors move, press buttons, or anything like that. And after every action, the agent will receive a reward. So just a number that can be positive or negative. And then a state that we can also call observation. So basically the agent is something that sees, is able to act and to do things, and its objective is to learn what action to execute in which state, so that the sum of rewards that the agent gets is maximum. So it's a bit like training a dog, for instance. And what is interesting with reinforcement learning is that sum. So here is a small example of an agent that, for instance, because it's interested in the sum of rewards that it will get until the end of what we call an episode, it is able to sometimes trade short-term negative rewards for longer-term bigger rewards, for instance, and take shortcuts. In this case, this is an agent that gets wet, but prefers to get wet to take a short path than take a long path. And so usually we consider episodes, so that means that the agent will start, try to accomplish its task until some end. So after some time we stop the agent and we reset it, or maybe the agent has reached a goal and so we end the episode and we start another one. So it's really repetitive. The agent is performing several tries at trying to accomplish the task. So reinforcement learning is a little bit special because there is that aspect of performing actions. And so good examples of what we can use reinforcement learning for is basically any task for which we know what has to be done, but we don't know how to do it. So we cannot ask developers to create the program that does the thing. We have to have an agent that learns to do it automatically. And so an example of task would be, for instance, preventing traffic jams by managing lanes in a highway, for instance. So the agent sees something, it sees the cars, for instance, it acts, so it can open and close lanes. It is rewarded when there is no jam, and it is punished, for instance, when there is a traffic jam, and we don't really know how to do it. So we have to have an agent that tries by trial and error to learn what to do to minimize those traffic jams. The sort of related example that is not a reinforcement learning task is learning whether a traffic jam will happen. So this is more a supervised learning problem or a prediction problem. There is no concept of action. So learning whether a traffic jam will happen, what will be the weather tomorrow, or things like that, those are not reinforcement learning problems. So we should not try to use reinforcement learning agents to solve those problems. So now that we know what reinforcement learning allows to do, then so we have that agent and that environment, then what do we need to know when we want to apply reinforcement learning? So in most cases, applications of reinforcement learning will involve the design of a new environment. So agents exist. I will present one in this presentation. There are other agents that are available online, so source code is public. It's very easy to find agents, but then environments have to be designed. And in order to design an environment, we need to define a few objects. So first, it's what we call the set of states, or the state space. So what will the agent see? Will it see images? Will it see sensor readings? Will it see lights or things like that? So it's very problem specific. What is nice with reinforcement learning is that those observations given to the agent, they don't have to be high quality or human friendly, because there is no developer that will have to make sense of those observations. The agent will learn automatically using them. That means that, for instance, if you have a sensor that returns weird values that sort of measure distances, you can give that directly to the agent. You don't have to transform those weird values in centimeters, because you know that at some point there will be someone who will code something and that expects those readings to be in precise centimeters. So when we have defined what the agent sees, we need to define what it can do. In all the algorithms that I will discuss today, we always assume that what the agent can do is basically pressing buttons. So it has a finite set of actions, and it can just say, I want to do action 1 now, I want to do action 2 now, I want to do action 1 again, and so on. Then we need to define the reward function. So that's something that it can be complicated, but it's outside the scope of this presentation. So after every time that the agent does something, so it performs an action, we need to provide it with a number that can be 0, but it has to be non-zero in some cases so that it can be maximized. And that's basically what has the agent, what does it have to try to do. And finally, we have the transition and termination functions. So basically, the transition function just says what happens when an action is executed in a state. In the real world, good surprise, we usually don't need to make a transition function, because the real world is the transition function. If you apply electricity to a motor, the motor will turn, the robot will move. All of that is computed for you by the universe. You don't have to implement that function. The termination function basically says when an episode ends, so it can be a simple termination function, for instance, ending any episode after 150 time steps, or measuring some amount of time in seconds, or something like that. Then, just for the sake of completeness, there are two other aspects of an environment, but I will not give too many details because, well, they are quite specific. So now, when we apply reinforcement learning, when you try to apply reinforcement learning, there are a few challenges. And so this is also why there is still reinforcement learning research happening. So here I have an example of challenges with the ones in bold that are the ones I will focus on in this presentation. And so sample efficiency measures how quickly, so with how few trials and how few interactions with the environment, the agent is able to learn how to perform a task. This is important because when we have a robot, for instance, or a website or a mailing system or anything that learns to do something, we don't want that system to spend years and years before learning something useful. So partial observability arises when we have an agent that does not see a complete description of what is around it. So it doesn't have enough instantaneous information to make a good decision. For instance, a camera does not see through walls. And so the agent is unable to reason about what is behind a wall in front of it. I will not give more details about partial observability in this presentation in the interest of time, but in the manuscript, for which there is a link on YouTube and at the start of those slides, there is a whole chapter that discusses partial observability, how to address it in various ways, and then a contribution from me that helps with partial observability. Then we have multiple objectives and multiple agents. So multiple objectives, you have to balance several objectives in interesting ways. Multiple agents, that when we have multiple agents that learn at the same time in the same environment and interact. For instance, several learning self-driving cars that have to learn to share a highway, for instance. It causes many challenges, but I'm not focusing on them. And then more practical challenges. So safety and exploration are for me linked to sample efficiency. So you want your agent to learn quickly so that it doesn't spend time and money learning, and also it doesn't commit too many mistakes. And then we would like to avoid those mistakes. So if we can reduce them to zero, it's even better. And exploration, just how efficient the agent is at trying various actions in various states and not always trying the same dumb things. And then sensing and acting, so that's when the environment is not a program but is a robot. Well, at some point we have to make the robot or connect a computer to a robot. So many problems, quite problem specific, happen here. So how to talk to a motor, for instance, how to get images from a webcam. So at the end of my presentation, I will focus on those two challenges and then present the solutions that I have for them. Some of them are general to any real-world application. Some of them are quite specific but illustrative on the motorized wheelchair that I consider in my research. So keeping those challenges in mind, so I can introduce my contributions. So option observation initiation sets. This is the chapter of the thesis that I will not present in this presentation because it's not used then by the wheelchair, for instance. And that helps with partial observability in interesting settings. Then I have BDPI, that is a new reinforcement learning algorithm. It's quite a theoretical contribution, and that algorithm explores very well and is highly sample efficient. And because it is highly sample efficient, then it can easily be deployed on the motorized wheelchair that I will present. But I've heard other people applying BDPI to other real-world tasks, for instance, shunting trains, maybe drug design. I don't know how well it advances on that point. And those three contributions that I will present are then used by other people in the AI lab to do further research on more applications on the wheelchair, or maybe having reinforcement learning that takes care of a human. So on the wheelchair there is a person, but it's not only a wheelchair. So how to leverage that human to learn better and how to learn in a way that doesn't stress the human. And then explainable RL. So many people in the lab will start working on that. It's basically like we learn how to do something, but then it's nice to also be able to explain why am I doing this. So the agent is turning left. Why is it turning left? So that was for the broad overview of reinforcement learning and what it allows to do. So now we are entering the slightly more technical part of this presentation so that I can present my contributions. So there are three big families of reinforcement learning algorithms, really the main families. So what we call policy-based algorithms, they learn an actor. So basically they learn something, an object, that directly maps a state to an action. So you give the actor a state and it tells the agent what action it should do in that state. Value-based methods, instead of an actor, they learn what we call a critic, that basically measures or approximates how good is a particular action in a particular state. So it's not what action to do in a state, it's how good is that action or how promising. Then we have that last family of actor-critic. They basically learn both an actor and a critic. I will give more details later when I start my contributions. So basically, to give more details about those families, policy-based methods, they learn an explicit policy. So why explicit policy? It's because if you implement a policy-based method, or if you find an implementation somewhere, there will be an actual object that is the policy. So it can be a table, it can be an array of floating point numbers, it can be a neural network, it can be a database, something that maps a state to an action. And the way it's trained intuitively is by trying actions and then doing good actions more often and bad actions less often. So the training procedure will really play on how often actions are executed in some states until the agent is able to perform well. Value-based methods, they do not have an explicit actor. Instead, they use a critic that we also sometimes call a Q table or a Q function, Q for quality, that measures how promising is an action in a state. There are formulas to learn those Q values. They are in the manuscript if you want. I prefer to omit them in this presentation. Once we have learned those Q values, then we can choose what action to execute in a given state by just executing the action that has the largest value in the state. So we just, in every state, execute the action that is the most promising and that is the best action. What is quite technical but also interesting to position my contributions is that there are two families of value-based methods. So, and the difference is quite difficult to grasp. So on policy algorithms, they learn a Q function that basically evaluates a particular policy. So that means how good is an action in a state given that the agent will then do something. Of policy algorithms, they learn how good is an action in a state given the best case scenario, to be brief and intuitive. And so I can use an example of cutting a table in half. So how good is it for you to cut your desk in half? Well, an on-policy algorithm will look at what will happen later with you. So then the value will be completely different if you are a very good carpenter. And so after you have cut your desk in half, you will make a super nice other desk or something else out of the two pieces. Or if you are just a normal person and then the desk has to be like discarded because it's not working anymore. So basically the algorithm will look at what will happen in the future basically. An off-policy algorithm, in that case, will always say that if you cut your desk in half, it's very good because there is a possibility that something wonderful will happen later. So now with those two differences in mind, I can introduce my first contribution, that is the bootstrapped dual policy iteration algorithm, or BDPI for short. And it builds on an interesting aspect of actor-critic algorithms. So actor-critic algorithms, that they still have the environment, and the agent itself is made of an actor and a critic. And what usually happens is that what happens in the environment is used to learn Q values, so to train a critic using interesting algorithms. And then what has been learned by the critic is used to learn a good actor. And the actor is what executes actions in the environment. But then we can ask ourselves the question, like, this critic, does it have to be an on-policy or an off-policy critic? Because we have those two kinds of algorithms. And it turns out that in 99% of the existing actor-critic algorithms, for interesting reasons, the critic has to be on-policy. So we have no choice. But that also means that if the critic has to be on policy, it reduces the set of algorithms that can be used for the critic. So the question is it possible to have an actor-critic algorithm where the critic is off policy, that it learns Q star? And the answer is yes, and is at the base of my first contribution. So first, let's have a look at formulas just to see how things go together. So if we look at how policy gradient, so just learning an actor works, we have a formula. The details of the formula are not relevant, but we see that we have a pi here that appears. This is usually how we call the actor, and then we have something here that is just a sum of rewards. What matters is that we just have an actor here that appears in the formula. When we have a conventional actor critic, we see that it's almost the same formula. So we still have the actor, and the sum of rewards is replaced by the output of the critic. So we see that what the critic has learned is used to make the actor better. And it turns out that mathematical properties of this formula mean that we really need to use an on-policy critic here. If it becomes off-policy, problems happen. The actor completely degenerates. In some cases, it can even crash the program, like imagine. But what is interesting is that there is another approach at doing actor critic, and that's using something that is called conservative policy iteration. And we see that the formula is completely different. We still have the actor, we still have the critic, other symbols around them. What is interesting with conservative policy iteration is that even if most people using it use on-policy critics for some theoretical guarantees that it allows, the algorithm does not break down if you use an off-policy critic here, because the formula is different. And so that's the cornerstone of BDPI, conservative policy iteration, and here using an off-policy critic. So when we look at the complete BDPI, so all the details, code, examples of implementations are in my thesis. So it's basically actor critic, but it uses conservative policy iteration to train the actor instead of policy gradient. So it's using this formula instead of this one. And then instead of just one critic, it learns several ones. So that helps with exploration, that helps with the agent reasoning about its uncertainty. The critics themselves, because we have conservative policy iteration, can be off policy. So it opens up a whole lot of different algorithms that we can use to learn the critics. And one of them is called clipdqn. It's a very good algorithm, basically. It has nice properties. And in BDPI, an extension of clipdqn, so things have been changed. And so it's even, well, better, if I can say so. It's more sample efficient. And so we see that there are those 4 components that make BDPI. So we have a new reinforcement learning algorithm. Whenever we do research, we have to evaluate whether that new algorithm is better than the previous ones. And so for that, in reinforcement learning, we use what you call benchmark environments. So it's a set of environments that researchers can freely choose, in which the agents can learn. And in the case of BDPI, the evaluation is done on 4 environments. So here it's just pictures of the environment. What do these environments do is not really relevant here to the discussion. What is important is that they're standard benchmarks, so they're available online. Anyone can compare their algorithms to BDPI using those environments, and they're also very different from each other. So for instance, this first environment table is really difficult to explore in. So the agent really has to be curious and to look far away in order to discover what to do. Here, Lunar Lander has complicated dynamics. There is gravity involved, so it's a complicated task. Frozen Lake is what we say extremely stochastic. So that means that every time the agent tries to do something, something quite random will happen in the environment. So the agent cannot really be sure of what will happen if it executes an action. And finally, Hallway here is 3-dimensional. So here the agent just observes images, 3D images of what is happening in the environment. And that's also quite challenging. So we have that wide variety of environments. And what happens is that, well, we get good results. So first, how to look at these plots. Those are what we call learning curves. So the idea is that on the x-axis, we count how many episodes have been tried by the agent. Here it's in thousands of episodes, so 0.5k is 500 episodes. And on the y-axis, this is basically the sum of rewards that has been obtained by the agent on a particular episode. And so we have a line that we hope goes up, so that means that the agent is getting better and better over time. And we also hope that it goes, well, very high, so that the agent ends up being very good. And we also want it to increase very soon, so on the left of the graph, because that means that the agent is quickly having a very good performance. So we have a selection of algorithms here. And, well, I will not enter into details of what those algorithms are. What matters is that the black line here is BDPI, and we see that on all 4 graphs, that line is always on top of all the other lines. So this line here is a slight variation of BDPI. So it's also BDPI. And so this is what allows to see that BDPI is more sample efficient and learns better policy than other algorithms. And so this is what shows that BDPI is better than them. So that's it for BDPI. So now we can, and also the more theoretical parts of my presentation, now we can go more towards an application, go towards that motorized wheelchair and other real-world applications. So first, BDPI works really well, but this is also an algorithm that can really put a computer to its knees. So this is a pseudocode of BDPI, so just a summary of what it does. What matters is that we have four loops all inside each other, and basically every time step, so every time the agent wants to take an action using BDPI, so many things will happen. This will turn a very large amount of time, and this is something slow. Basically, well, the agent will need 2 to 3 seconds to take an action. So it seems brief, but if you need 2 to 3 seconds to move slightly like a wheel in a car, that's not acceptable, for instance. And so we need to find a way to make BDPI just plain faster. And so, well, and this problem is even more important in the real world, because simulated environments, so when the environment is a program, well, they can be stopped at any moment. So when the agent executes an action, code will run here in the environment, will compute a new state and a new reward, and then the agent will execute. And when the agent is executing, well, nothing is happening in the environment, and basically the agent has an infinite amount of time to take an action without any dire problem. But if this environment here is the real world, so it's a robot, for instance, when the agent is thinking, well, the real world will not stop. Inertia will make the agent still continue to move. If the agent is controlling a website or something like this, well, users will continue shopping, they will continue reading their emails, they will continue to do anything while the agent is choosing an action or learning. And so that can lead to problems. Illustrated here, and also with more details in the manuscript, is that at some point the agent will produce an observation, tell the agent, oh, this is now what is happening, and the agent has to react to that and select an action. All the time it takes to select that action, so here the difference between those two arrows is time during which, well, the agent will not see any updated reading from the environment, so it's completely blind in that time, and it does not have effect on the environment, so it cannot intervene on the environment. And so if this sort of lost time here, that reaction time, becomes too long, it can prevent the agent from acting correctly. It introduces delay, but it also prevents the agent from knowing the effects of its action, so it can really prevent the agent from learning. That can be important in some real-world applications of reinforcement learning. So the solution to that is, well, a little bit brute force. It's basically to split BDPI in many components that can all run in parallel with each other. So this is a sort of exploded view of BDPI. Every box here is a component that runs in parallel with other components. So implemented in Python, those are all processes so that they can run concurrently. And so what is important is that there is one process here that is dedicated to just get states from the environment and introduce actions to it. So it's basically just reacting as quickly as possible. This process just selects an action as soon as the environment gives a state, and this is what minimizes this lost portion. And in parallel to that, stuff is happening. So for instance, all the critics, the actors, they're all trained in parallel. That allows to leverage modern multi-core machines. So it's not critical to minimize that lost portion, but this is an added benefit that the agent will learn better, quicker. So now, because we introduced something, we have to evaluate that thing. And for that, I'm introducing a new environment that is called the virtual office. So it's inspired by the ground floor of the building in which the VUB AI lab is. So it's the experience center. It's a large office that has tables and so in it, and that allows to show the demonstrations and everything that is made by the AI lab and partners lab, like for instance the robotics and so on. And in this environment, we have an agent that is able to rotate on itself and go forwards, and it observes the distance between it and the closest obstacle in a field of view. So this is quite a complicated environment. So it's more complicated than the 4 ones on which BDPI has been implemented first. It's fully described in the manuscript again. And what we can see when looking at learning curves is that, well, again, BDPI is on top. What is also interesting is that if we look at a small amount, so here on the x-axis it's time steps, so it would be about like 30 episodes or something like that. So the line that corresponds to BDPI goes up very quickly and 3 times faster than the closest competing algorithm. So BDPI is very sample efficient in this challenging task. But then we see that it's sort of confounded. So we can ask ourselves the question, oh, okay, but then if we have time to train the agent, is BDPI really the best algorithm? And so we can look at the other algorithm. So it's the same curves, but here the x scale has changed. And the idea is that we see that if we continue learning, the line of BDPI is still increasing. And so it becomes much better than the 2 other algorithms. And so whether we have time or not to learn, BDPI is always the best solution. So this is really what we can take out of this plot. And so because BDPI is so sample efficient, it opens like the possibility to apply it to real world robots without a simulator. So learning is directly happening on the robot. And so in my thesis, I have applied BDPI to this motorized wheelchair. So this motorized wheelchair, we received it from Invacare, so it's a company that manufactures motorized wheelchair. It is available in the market, so anyone can buy it. And also, it has not been made for BDPI, it has not been designed for us, and it has not even been designed to be controlled by a computer. And that makes using it quite challenging, because even like how do you control it? That joystick, for instance, like moves the wheelchair, but in a very unpredictable way. There is a large amount of inertia. There is no sensor on the wheelchair. So from a purely robotics point of view, it's very challenging to use that wheelchair. So what it will be used for is to learn how to reach the main entrance of the experience center. So this is a photo of the experience center, so that area where you have demos and different things that are shown to visitors of the AI lab and collaborating labs. And we see that there are tables. Those tables are constantly moving because this is also a meeting room, and so well, it always changes. We cannot really map that office, and we cannot just plan in that map, for instance, because everything is moving so much. But so this is a view of the environment for that wheelchair. And so, as usual, when we want to apply reinforcement learning to a task, we need to make an environment for it. So we need to define states, actions, rewards, transition, and so on. And so in the case of the motorized wheelchair, the states, basically what the agent will observe, is something that will look like what was produced by the virtual office environment. So a webcam in front of the wheelchair looks at obstacles, well, takes images, uses an algorithm to compute the distance between the wheelchair and obstacles like at different angles, and gives that list of numbers basically to the agent as observations. The actions, there are 4 actions. So basically, and every action corresponds to a position to which the joystick is put. And so, for instance, there is one action that allows to go forwards, one that allows to go left, one that allows to go right or to stop. In this case, every action corresponds to putting the joystick in a specific position for a third of a second. Then the reward, I will give more details later, but basically +10 or -10 depending on what happens. Transition function easy, provided by the universe the wheelchair is moving, so there is no simulator involved. And the termination function is also quite simple. Every episode stops after 150 time steps. When we divide this, we get 50 seconds per episode. And then the initial position, it's always the same. So at the end of an episode, I manually take the chair and put it back basically where it is here in this photo. So this is quite far from the main entrance. So now 2 quite technical slides about what has to be done in order for that wheelchair to be controlled. And so we need to define how to act. So how can actions that are just numbers for the agent, how they are transformed into something that makes the wheelchair move. And for that, there is a pipeline of devices. So the agent runs on a powerful desktop computer, sends actions over Wi-Fi to Raspberry Pi that is taped to the wheelchair. That Raspberry Pi has like a server that waits for commands over Wi-Fi, sends them to an Arduino over USB. That Arduino is connected to what we call a DAC, so something that takes commands and transforms them to voltages, and those voltages are injected here in the joystick. So there is actually soldering involved here, and basically by injecting voltages in the right locations in the joystick, it allows the wheelchair to believe that the joystick has been moved. So the joystick on the wheelchair is not actually moving, but the chair is moving as if someone was moving the joystick. So that's what we call the acting side. So how to get like the chair to move when actions are executed. So now we have the sensing side. So from that webcam that is in the front of the wheelchair, how can we detect obstacles, compute distance measures, and give them to the agent? So the algorithm is quite simple to detect obstacles. It's just based on abrupt changes in texture. So the floor has a uniform texture, and anything that has different texture is not the floor and will be seen as an obstacle. This is quite a basic obstacle detection algorithm, but I would like to stress the fact that it's interchangeable. So my research is not about detecting obstacles, it's about reinforcement learning. If someone has a better obstacle detection algorithm, then yes, it can be used. It will probably lead to an agent that performs even better. So this obstacle detection algorithm, we have tried it at numerous occasions. We have, well, the chair has been shown to different people at different places, and in these three environments, it was working. So we see that this is sort of uniform wooden floor, this is carpet, so it's also uniform, and this is tiles, so the grout lines between the tiles are not too big, and so it's possible to consider that this is a uniform floor and this is not the floor. In this case, it was not possible to use our obstacle detection algorithm because those tiles that have a different color, they were confused with obstacles. Something else that is important when we have a real-world agent is safety. So there are many approaches to safety with reinforcement learning. There are people who are specialized in it. What I focused on is what we call backup policies. So the idea is that in addition to the agent that learns, and so that can at some point make mistakes because it has not yet learned perfectly, there is an additional component that looks at the state and will override the action of the agent if need be, or it may also prevent some actions from being executed. In the case of the wheelchair, the space here of pixels is divided into 3 regions, and basically that red line indicates where is the closest obstacle, so the closest from the bottom of the image. If all the obstacles are here in the top portion, then nothing is happening, the backup policy is happy, there is no obstacle too close to the wheelchair. Now, if there are obstacles in the left, center, or right regions, the backup policy will take over and you will, for instance, prevent the agent from turning towards an obstacle. So all the details and all the conditions of obstacles in the left, center, or right are in the manuscript, but that's basically what happens if there is an obstacle too close. The backup policy may even forcibly make the agent move away from the obstacle. So here there is a small plot because, again, when we introduce something, we have to evaluate its impact. So this is a simpler environment in which the exact same backup policy has been introduced, and the idea is to verify, well, if the backup policy influences the actions taken by the agent, does it prevent the agent from learning or does it impair it? And fortunately the answer is no. So again, all the details are in the manuscript. The maximum return that the agent can obtain in this simple environment is 50. We see that it almost reaches 50, and why not completely 50? Well, all the reasons are given. It's not because of the backup policy. And so we see that a backup policy designed like this does not prevent the agent from learning. So now, last component of that wheelchair, so we have the observations, we have the actions, we have the backup policy, is the reward function. So there are 2 components to that reward function. The simplest one is that whenever the backup policy has to do something, the agent is punished. So a reward of -2 is given per second in the backup policy. So that entices the agent not to get too close to obstacles because it gets punished when it is too close to obstacles. But then we want the agent, so this is also a map of the experience center. So virtual office is inspired from the actual map of the experience center. And we want the agent to reach this location, And so how it's done is basically using manual reward. So I'm pressing a green or a red button depending on what the agent does. And so the space is divided in regions, and whenever the agent crosses here a demarcation between one region and the next in the right direction towards the goal, it gets +10, and if it crosses that same demarcation in the other direction, so away from the goal, the agent gets a reward of -10. So it's punished when it moves away from the goal. And with that, it learns to reach the goal, and here this is what the arrows are showing. So it's the different paths that the agent takes to go to the goal. And finally, so the main result of this thesis, it's quite a simple plot compared to the other ones, but that's really the main result. This is like over time, actual real world time, this is 1 hour and 40 minutes. How well can that wheelchair learn to go to the main entrance? And we see here a learning curve that goes up, still increases, and almost reaches the human level. So the human level is me, so I know perfectly the experience center and everything, with a joystick guiding the wheelchair with the shortest path to the main entrance. So it's very difficult to reach that human level. And you see that the wheelchair itself manages to do it quite well. And I have a small video that shows what the wheelchair is doing. So this is the wheelchair being started, and so we see that it turns towards the right direction, avoids the obstacles, and then it will go forwards toward the main entrance. Going forwards is not easy, because that agent may at some point choose to turn left, for instance, and then get lost. So it's really nice that it can have a nice forward line. We see that it's not very fast, so that's mainly for safety purposes. Well, that wheelchair is very heavy, it cannot move too fast. Also, the agent is not yet completely certain about what to do, so it hesitates a little bit. And we will shortly see that after 50 seconds, so the wheelchair avoids its last obstacle and then it stops because the 50 seconds have elapsed. There is a button to ask the wheelchair to continue, and it eventually reaches the main entrance. So we can see that it works. So that that concludes my presentation. Well, what we can see from that result is that it is a real-world robot. So it's a real-world application. It was a robot, but it can also be applied to things that are not a robot. It's a real-world robot in a real-world environment with real-world challenges, electronics and things like that. The wheelchair has not been designed for a reinforcement learning agent, and still it learns. And so it learns a policy that is clearly better than random, so something has been learned and is almost human level. So ideally with reinforcement learning, we want to exceed human level, but well, this is still fundamental research applied to a motorized wheelchair, so getting almost to human level is, I think, good. And then from that, well, we can also point at future work directions that build on BDPI. And one of them is going to the goal from any initial position, so not always starting in the same location. What is nice is that it's now possible, so the wheelchair is able to find its way in the experience center to the main entrance. Further increasing the sample efficiency, because, well, an agent is never sample efficient enough, so there is, well, already research in that direction happening. BDPI with continuous actions, so I refer you to the manuscript about information about continuous actions that just allows more tasks to be learned. This is also something that is starting to give its first results. And then other aspects of real-world applications like websites, or basically when we want to have a machine or something that does something autonomously, it's usually because it interacts with humans, and so we need all those aspects. So that concludes my presentation. Thank you again for the interest and for, well, the 28 people who watched this presentation, and I will now let Professor Manderick continue with the ceremony.
Okay, thank you for your presentation. Now we will go over to the questions, and Denis, I would like to ask you that you get your PDF ready, because some of the questions are referring to the text.
Okay, I will see if I have my PDF somewhere.
Yeah.
It is on my phone.
I will be able to read them. Okay, so now it's time for questions, and maybe for the general public, I should mention that Before the public defense, we had the private defense, which was attended by all thesis committee members. But for several reasons, 2 of the externals could not be present today. We have the tradition that we start with the external examiners, and we use distance as a criterion to rank them. So the first questions will come from Professor Manuela Veloso. She's professor at Carnegie Mellon. That's in Pittsburgh, Pennsylvania. By the way, she's Herbert A. Simon University professor over there. And Herbert Simon was both Turing Award winner and Nobel Prize winner in economics. And for the moment, she's on leave heading the JP Morgan AI lab. And the questions you have sent to me are quite general. So the first one is, Denis, if you would start your PhD thesis over again, what would you do differently this time? And what have you learned?
Well, so I have many answers to that question. It's mainly like in practicalities and things like that. So for instance, I'm now advising new PhD students at the lab with all that. I would say that it's very important to talk to many people. Well, every PhD hears that when they join and they don't do it, but well, it's very important because good ideas come from discussion with other people, and it's also very nice to have people where you can say something like, I want something that does this and that person is able to put a name on it, so that then we can look for papers doing it, see what is already existing. So I would say that it's the main answer. I would also like to add the second one, that is publish early and publish often, like often trying to submit papers, because that also gets people looking at the work, criticizing the work. Currently, well, it's often criticizing the work. And then that also helps to steer the research in directions that will then be useful.
Okay, thank you. And then Professor Veloso had a second question. Can you share how difficult it is to change the robot platform, and how you expect your approach to be easily reproduced by other researchers?
That's a very interesting question. So indeed, when we have robots, well, it raises the question of, can anyone else do it? So in the case of my research, what is nice that the main contributions are the BDPI algorithm. And well, it can be used in any environment. I've presented 5 simulated environments in this presentation, plus the wheelchair. Now, the wheelchair itself, it has the nice property of being available for sale, so anyone can buy it, but then has to change the joystick. And then to put that on another robotic platform, I would say that the difficulty lies on the robotics level, for instance, is to have a way to execute actions on the robot. But BTPI itself, so even its configuration, what kind of neural network to use and things like that, is quite generic and portable. So I have the feeling that on the algorithmic side, there is not much to do.
Okay, thank you. So these were the questions of Professor Veloso. Then I go to the questions of Professor Babushka. So he is professor at Technical University Delft. And he has 3 questions. The first one is, okay, why do you need reinforcement learning to solve the wheelchair navigation problem? If you would use standard obstacle avoidance algorithms, that would also be right. Don't you think so? So can you argue why you need reinforcement learning for this application, why it cannot be done by standard obstacle avoidance algorithms?
Well, this is also a very good question, because indeed that wheelchair can, well, so it's not using reinforcement learning to try to improve the wheelchair. I would say that my research is more using the wheelchair to improve reinforcement learning. So the idea is to show reinforcement learning is able to do that, but I'm also a strong proponent of not using reinforcement learning when you don't have to. So if someone has to make a self-driving vehicle and is happy with the current planning, so not reinforcement learning based algorithms, then just go for it. Now, what is interesting is that it's also possible to mix reinforcement learning with something else. For instance, the action of a reinforcement learning agent can be something that controls a car for 10 minutes, for instance. So this is something that is perfectly possible. So that reinforcement learning is only used for the part for which we don't have existing solutions.
Okay. Then the next question starts with a quote from your text, page 132, but I will read it. So while we deploy our system on a motorized wheelchair, most of our contributions in this chapter also apply to non-robotic systems, such as reinforcement learning-based recommender and decision systems, industrial settings, etc. And then the question is, how can you make this claim upfront already in the introduction? And what specific results of this chapter support this claim?
Well, unfortunately for the specific results that well, to my knowledge, they are not published yet. I wanted to have reference for that, but it's not here. So if someone knows about the train shunting problem, I don't even know if I can say who is doing this, but well, there's been like interesting results obtained there. So now the statement itself is not really a statement that, well, it can be applied to any problem. It's just that the theoretical contributions themselves, so the asynchronicity, the fact that actions have to be executed very quickly, the reaction time is important. Those are known problems in other applications, and sample efficiency is also something. So I have a colleague who at some point was using reinforcement learning to detect fraud in credit card systems, and his main objective was also sample efficiency, because, well, the amount of fraud is not that large, and so we don't have that much data to learn from, and we cannot let too many frauds pass through because an agent is learning.
Okay, thank you. And then for the last question, you should show your PDF file if possible. It's about an equation 3.2, which is on page 69.
I can go to page 69, but unfortunately I don't have the PDF on the computer I'm using here on Teams. So equation 3.2, yes, so I have found it.
I don't know if I can share my, because I have it.
You can share your screen, but then people on YouTube will not see what you are sharing.
Okay, so then just look at the equation 3.2. And the question is if the policy pi is a neural network, as stated below that equation, what does that equation mean? That's the question. And then he also states that the equation does not seem to be correct. Pi of s, the value the network outputs for, cannot be assigned to any other value, as the left arrow in equation 3.2 suggests.
I would say that it's probably a matter of notation, because I don't see where the equation may be incorrect when looking at that. So there is indeed a pi of s that appears in the equation and on both sides of the arrow, so it means it's updated towards a new value. So, well, for YouTube people watching us, it's basically doing a variable plus equal something that is happening. So this is perfectly possible. Now, what was the question about the neural network thing?
Yeah, but I think it has to do with the fact that if pi is because you say with pi the actor, a neural network. Yeah, and then the question is, if pi is done by a neural network, then you cannot make an assignment like this. I think that's what is meant by the question.
I understand, yes. So that was the same kind of question as there was for equation 3.1, and the answer is the same. I just did not copy paste the text in the thesis. So yeah, it's an abbreviated notation that shows that the neural network will be trained towards those updated values. So yeah, how it is implemented is that the left hand side of the arrow, that new pi of s, will be in an array, in my case a PyTorch array. And then the neural network pi will be trained using the states as inputs and that left hand side of the arrow as targets on the mean squared error, so exactly as with the critic, for a number of training epochs, like 20 or 30 in my experiments, and this implements that. Basically, BDPI is using neural networks just to store values as we would do in variables.
Okay, thank you. So these were the questions of the examiners external to the VUB. Then we have an external examiner at the VUB of the Faculty of Engineering. And I have to apologize to Professor van der Borgt because first time I mispronounced his name. So Professor van der Borgt, by the way, he's professor in robotics. So do you have a few questions for the candidate?
So congratulations already, Denis, with your nice work. It was very courageous from you to leave the virtual world and spend quite some time on experimenting with real robots and not just buying an existing robot, but turning a platform into a robot. So working on the hardware, electronics, so basically hacking the wheelchair. So imagine you had a robotics engineer available. During your PhD, what would you have asked to develop to improve the capabilities of your system? And so which requirements you would have imposed to that robotic system being the wheelchair?
That's a good question, because the answer of that question is basically a mail that I was planning to send you right after the defense.
Yeah, I already know.
And so basically, well, so now most of the work is done, but the main problems that I had was that really that reverse engineering, things like that. So ideally, for a pure software reinforcement learning researcher, there is the OpenAI GYM API that defines how to execute actions and get states, and basically asks an expert roboticist from make this work on the wheelchair. So currently there are main problems because I'm not expert at all in robotics. There are a few limitations. The control of the wheelchair itself with the joystick, it has problems, inertia and things like that, because the joystick itself is an open loop system, so the wheelchair is not aware of the rate of its wheels turning. And so solutions to that would be very welcome, because currently it leads to that sort of jagged movement when the chair is moving, and also the obstacle detection algorithm and whole localization of the wheelchair. So I've spent countless hours like Googling solutions to that, but it's Googling. It's not like having a career of roboticist behind me. So those are the main points that are currently suboptimal.
So would you replace the webcam with, I don't know, a LiDAR system or a depth camera, or is a webcam you think suitable?
A depth camera would be better, I think, because at the end we don't care about colors, we care about is there an obstacle there, and the webcam, well, it's not what it produces. Now for the LiDAR, well, it seems a little bit expensive, because the main point that I want to sell also with that wheelchair example is that, so it's very cheap, like not professional hardware used on it, but still the agent is able to learn. And that's also to show that if you have a learning agent, you don't need to have very precise controls. You don't have to have things that are easy to model. For instance, the agent can make do with what it has. So I would refrain from very expensive sensors, but I am open to anything else, basically something that would be like a few €100 top, for instance.
Yeah, LiDARs are still expensive. On the other hand, due to the self-driving industry, there is also a strong push from industry to make it much cheaper. Because of course you cannot have multiple of those LiDARs on a driverless car when they cost €100,000 and it's already the price of the car. So that's why there is a strong push to reduce them, but there are other visions, like in Tesla, that they do it purely on computer vision, and they're, for example, not on LiDARs. Okay, that was my last question. Thank you a lot.
Okay, thank you very much, Professor van der Borgt. Now I'm looking at the Professor Gonzalez Bosch, to see whether she has some questions. I think your camera is not on. Sorry, your mic is not on.
Hello?
Yeah.
We hear
Okay,
you.
sorry about that. Yeah, well, I will ask you a small technical question, and then if time allows, I can ask you a couple of questions on future work. So my first technical, not for the AI part, but more on like your deployment on the wheelchair. And you made a nice effort as well to revisit parts of chapter 5. And where you explain us how did you move the BDPI for the wheelchair. And I appreciate the part where you explain about the race condition, for example. And there you touch upon one aspect that I would like you to further comment. You explained that if there will be a problem of a race condition that leads to an invalid sample, and that these invalid samples are actually have a negligible effect on training. And I was wondering, you mentioned for a particular figure where we can see that invalid samples have a negligible effect, and I was wondering if you can elaborate a bit more on how do you generate invalid samples and how we can, from that figure 5.13, I can see like number of invalid samples that were discarded by the algorithm. It was not entirely clear to me.
So it's a good question, because indeed on that side I maintain brevity, so I can give more details. So what I mean by invalid example is that the addition of a sample in the experience buffer, so we have a state, an action, a next state, a reward. It's done component per component, so at some point we may have a new sample that has its state that is set but not yet its action, and if sampling from the experience buffer happens at that time, then we have a state that is not correctly matched to the action that happens in that state. So it's not like random values, it's just improper states with improper actions or rewards. And so why I believe that it has no effect, there are two reasons. So the first, a practical reason, is the hallway experiment with or without multi-threading. The learning curves are indiscernible. So that's sort of empirical evidence that if that happens, those invalid samples, it doesn't have an impact on learning. And so now why can it not have an impact on learning is that BDPI use large batch sizes. So every time the neural network is updated, there are like between 512 or 1024 samples sampled in that experience buffer. And if one of them is incorrect, then it's only like statistically 1 in 1000 that is incorrect. And the way that neural networks will learn, they always try to, well, basically please everyone, if I can say so. So they will learn a way to learn that is good on average for all the samples. So the 1023 samples that are correct, and then that other sample will not basically completely destroy what the network has learned, and in the next time step it will learn with other samples, and that error will probably average out.
Okay, so for my questions on the future work, well, one is I was a bit surprised to see that in your revised chapter on conclusion, there is actually no related work directly points out to continue the work on the real world. It seems that most of the work is on the algorithm or applying to other scenarios by some of your colleagues. So you did these experiments. I think that you started with a wheelchair according to the text in 2016-17, but by now we see an evolution on microcontrollers. So basically the microcontrollers are getting, in a certain sense, even though they are reduced, are getting smarter, that can run deep learning, or they have deep learning capabilities. So you have the ESP32, you can run there, you can have TensorFlow programs run on an ESP32 microcontroller, and this is something that has half giga of RAM and 140 megahertz. So how do you see your BDPI working into these smarter but still microcontrollers? So my ultimate goal will be to remove the fact that you need a Threadripper on your wheelchair. So there are two. Do you think that you will need to strive to a different kind of theoretical framework or different kind of algorithm? Or do you think that it's a matter of taking your current algorithm, implementing in TensorFlow, running it on the SP, and then only work at the software to make it optimal for a machine that has half a giga of RAM and 144 megahertz?
So currently BDPI is very compute intensive. So that Threadripper machine, it has 32 cores at almost 4 gigahertz. So there is a long shot from the ESP32 that you are referring to. Now, well, in that regard, BDPI doesn't try to do everything. So currently its sample efficiency comes at the cost of compute efficiency. But if you have a microcontroller system, that happens usually, for what I know, microcontroller systems are used in what we call fast sampled systems. So there are thousands and thousands of actions executed every second. In that setting, well, there are so many actions and so many samples that we don't need sample efficiency. And so we can use simpler algorithms like vanilla policy gradient, for instance, that are very quick to execute. And I have found at some point an Arduino implementation of policy gradient, so that runs on an 8-bit microcontroller that is even less powerful. Now, I still hope to have BDPI work directly on a robot without a desktop, but I would more envision like using those Tegra boards, so made by NVIDIA, so small GPU, a few somewhat powerful ARM cores at a few gigahertz. So it's just a matter of being able to train a neural network fast enough.
So if could your work also, for example, if you think about broader applicability, could your work help, for example, imagine that the head of somebody doing home robotics like Roomba, the Roomba company comes to you. Could your work, for example, in this sense, make that Roombas clean, I don't know, faster, more efficiently? How do you see portability towards already home robotics that they are already happening nowadays, for example?
It's a very interesting discussion, because so what is nice is that even if BDPI is compute intensive to learn, once a policy, and there is only one policy, is produced, executing that policy is extremely fast. So if learning happens in a factory to make a super smart Roomba, and then the policies are shipped with the robots, you don't need compute power on the Roombas. You could also maintain a sort of learning on the Roomba, so you pre-train them in the factory, or maybe the user could install a program on a computer and then pre-train that for some time, and then have a sort of continual learning still on the Roomba, but that will then be much slower because the robot, well, its embedded computer will be slow, but also once you want your Roomba to slowly adapt to your home, if it takes a few days, it's not a problem. So the main point of that wheelchair is that it learns something very complicated in 1 hour and 10 minutes, so it's shorter than this presentation now, like the wheelchair would have learned if it had started when the defense started.
Okay, so the last question on future work was in this human loop where you said that there will be people working on. I was wondering, does this also touches upon, or does it make sense to actually allow human inputs on the backup policies? And how do you see, if you can elaborate on the research lines for the human in the loop?
It's a very good question, very interesting answer that should be provided by my colleague Hélène Plesnier. So I will not really give an answer for her. You may have to wait for her PhD defense for that. But basically there are several ways to empower the user, as she says, so that if you have a learning agent, if it's unpredictable, it's really stressful. And so it's nice to have the user be able either to hint towards what should be done, prevent actions from being executed, see the backup policy, intervene with the backup policy. She has developed algorithms that allows to do that. It's built on BDPI, by the way, that allow to do that quite nicely. But well, it's outside my area of expertise.
Okay, thank you.
Okay, thank you for the questions. Now I'm looking at the supervisor, if she has questions or not. If not, then we will go to the public. So, Supervisor, do you have some question?
Well, maybe a small question to Denis, because he said in the presentation the wheelchair is always starting at the same starting position. So my question is, what is then the next challenge if you want to make it start from different starting positions?
So it's mainly a challenge of partial observability in this case. So because the wheelchair doesn't see what is happening behind itself, it means that if you start it just in a corner, it will just see the walls in that corner, but that doesn't tell it which corner it is, because there are many corners in the room. And so basically in that case, the wheelchair has to learn to turn away from the corner, and then it will see something that is more informative about what is happening. So that goes back to also my research on partial observability. And this is really the theoretical challenge, that if you take that wheelchair as is and put it in random positions, it will have a very hard time learning because it will constantly get lost and not recognize where it is. So again, now some unpublished research allows that wheelchair to do that, but it's basically, it circles around tables and, oh, no, I know where I am, and then it goes to the goal.
Okay, was that?
Yeah, okay,
yeah.
Thank you.
Okay, maybe before we go to the public, I have a short question. You talked a lot about sample efficiency during your presentation. Now, if we look at biological organisms, we are also doing reinforcement learning. And if you would look like, for instance, a rat and a maze, yeah? I mean, what would be the sample efficiency of a rat and a maze compared to what your robot is doing? Because if you want to approach general AI, then we should come much closer to what biological organisms can do. So have you any indication about the comparison of sample efficiencies?
The question is very interesting because to my knowledge, we don't really know. So I've seen that there is ongoing discussion. So if you put a mouse in a maze, the mouse will learn, well, to get out of the maze in maybe 2 tries. So 2 episodes, that's super, super high. But also if you put a newborn mouse in a maze, it will never get out. So basically, we must not see living organisms as learning new tasks from scratch with super high sample efficiency, just that they're extremely good at generalizing knowledge and transferring knowledge from previous tasks. And so why are people so fast at learning to play Mario, for instance? So this is an experiment that was done at some point. Is that because they have played many other video games, they know how to use a keyboard, they don't have to discover how to use their fingers when they have to learn to play a video game, so they can transfer all that knowledge. So basically, sorry, I don't really have an answer, it's just that we don't know.
Okay, so then it's time for questions from the public. And we will need Denise's assistant because the public is following via YouTube channel and I don't have access. So can you check whether there are some questions and if how many are there in total?
So there are, so currently I see 3 or maybe 4 questions. So I propose to read them in the order they have been posted.
Okay, fine.
So let me find the first question. So someone, because everyone is using pseudos, someone is asking whether other reinforcement learning algorithms have been evaluated on the wheelchair. So that's a very good question. And the answer is yes, but it's not in the thesis. So the reason why it's yes, because, well, the whole idea is to make that wheelchair work also, and so if another algorithm is much better than BDPI, then using BDPI would be a loss of time for that particular wheelchair project. And so I have tried PPO and Actor, so the 2 other algorithms that are also compared to the other well, environments, and basically they produce flat lines. So it's not really flat line. Eventually they would learn to do something, but their sample efficiency is so low. Oops. So this is not something. I will go back to that slide that shows that. So this is a late result, so on an environment that looks like the wheelchair, and the idea is that the wheelchair runs for a very short amount of time, and so we see that PPO and Actor, they don't learn anything in that time, and that these 30,000 time steps would, well, be equivalent to hours and hours of running the wheelchair. And so in that experiment, I let the wheelchair basically run for 3 hours each, and there was no discernible learning that happened. Another algorithm called Rainbow, so that is not mentioned here in this thesis, learns something, but that something was degenerate. So basically the wheelchair was turning in circles. And why was it doing that? Because then it never hits obstacles. And so it learns to basically be extremely afraid and not go close to obstacles, but also not towards the goal.
Okay, so that was the answer to the first question.
So I will also check if there is like a second version of the question that comes after my answer, but we have that 30 seconds delay. So a second question is, what kind of practical implementations do you envision for a real-life application of the wheelchair? And so this is also an extremely good question because I don't remember if it's in the final manuscript, but the idea of that wheelchair is that it would be useful. So I've talked to a person who sells those wheelchairs to disabled people, and he said, well, it's super useful because even the smallest task would be really useful for disabled people. And he says, for instance, some people shake too much, so they cannot use the joystick efficiently. Something happens outside and they want to go to the window, but it takes 10 minutes to go there. So by the time they reach the window, well, everything is done already. Same for the door, like the person has left the door for when the wheelchair user manages to reach the door. Those are relatively simple tasks. Basically the same kind of task as what is currently learned in the experience center by going to the main entrance, just going somewhere, can be learned in 1 hour. And so the practical setting would be a little bit like what we do when we buy air conditioners, like well, professional air conditioners. We buy the thing and someone comes to set it up. And so the idea would be that when someone buys an AI-enabled wheelchair, a professional wheelchair trainer or a professional agent trainer, it sounds a bit like Pokemon, but well, basically it's that, would also come with a powerful computer in a suitcase, connect everything, teach the wheelchair to go in a few locations, go to the kitchen, go there, and then what Ellen is also working on is a nice user interface for that, to click on buttons and how to go there. And then once training is done, and it should take less than a day, so that means only 1 hour, 1 hour and a half per skill to learn on the wheelchair, then the professional trainer leaves with the powerful computer, puts the learned policies on the wheelchair, and the wheelchair is now able in the particular home for that particular person to do what they need. So maybe it's a bit a dream, but currently we are, well, getting there with still a few miles to go.
Okay, and then maybe, so you have 2 more questions left?
Yes, no, I see new questions.
Okay, but let's say that we take 2 more from the public.
Okay,
so, choice to you.
So I see one that is, so you mentioned that BDPI could be even more sample efficient, and so the question is how? That's a good question. It's basically my job now as continuing research on BDPI. So there are 2 aspects of reinforcement learning algorithms. So something that is somewhat simple to understand is what we call the hyperparameters. Like that, many values, many knobs that have to be set in the algorithm, how big the neural network, how many, and things like that. And currently, BDPI does not have those parameters optimized. So that means that the ones that are used, it's in the manuscript 32 critics, for instance. Why 32? Because it looks nice, because 16 did not work as well, and I have not tried 64. And maybe there is an optimal number somewhere. And BDPI is quite robust to its hyperparameters, so this is a nice property. So that means that if you get them wrong, it will still learn something quite well. But also I have the feeling that we can get 10 or 20% more sample efficiency by optimizing those hyperparameters. And then the second aspect is the algorithms themselves. So currently the critics of BDPI are learned with an algorithm called ClipDQN. The algorithm is already a few years old, and so maybe better, greater, more sample efficient DQN family algorithms exist and could be plugged instead of ClipDQN to have critics that learn faster, and so the actor would learn faster, and so BDPI on its own would be faster.
Okay, and then maybe a last question before the deliberation. Okay,
so I don't see a last question, so I'm just double checking.
Okay.
So if someone, I'm also a little bit slow by doing that because now people on YouTube hear that I'm not seeing other questions. So if I'm missing a question, don't hesitate to type it again. But I don't see other questions.
Okay, fine. Then let's, okay, the committee has to deliberate. And for that, we have to go to another meeting. And now I want to be sure that we do this technically good. Maybe the easiest is if we turn off our mic and camera in the current meeting and we join the other one. I have sent a link to you like a bit more than an hour ago. Okay. Is that okay?
Yeah.
Is that okay for everyone? So then we meet on the other side.
Yeah, they are muted now. So I will tell you if I hear anything. Currently, I don't hear anything. I don't see anything. I can also take the opportunity to answer extra questions. So I see one, for instance, like, is BDPI, like, should it be considered the to-go algorithm? It's a good question. For my experiments, when you have discrete actions, so that is also the technicality of whether the actions are discrete or continuous, usually BDPI works better than the other algorithms. It's more sample efficient. So I would say yes, but I cannot guarantee for every problem. So usually when I use BDPI on something, it's better than the other algorithms. So currently BDPI cannot be used with continuous actions. It's just that in the center of BDPI, I don't know if it's visible somewhere on a slide, there is an argmax over actions, so that requires the actions to be enumerated. Well, it's the greedy function here that does not exist with continuous actions, and so if you have a problem that is with continuous actions, then BDPI cannot be used, and in that case I would go towards the soft actor critic that is currently considered the state of the art. So usually the deliberation is 5 to 10 minutes. If anyone has a question. And then I think that it's done. So I see that we are 21 watching the stream, so it's sort of reaching the end. If someone has something else to do, well, it's a YouTube stream, so that also means that if you miss something, you can easily go back in the stream and then rewatch it, or maybe like go back tomorrow or something like that. So there is a question about, well, actually people in YouTube see all the questions, but still, a question about, can BDPI be used in dynamic environments? It's more like a theoretical question about reinforcement learning. So BDPI doesn't make any extra assumption compared to what reinforcement learning agents usually do. Now, the question of a dynamic environment is a tough one, because depending on how dynamic it is. So for instance, there is the concept of drift in the environment. So that means that the environment is slowly changing from something to something else. Can be, for instance, the sun is setting, and so lighting conditions are changing, and the agent has to adapt to it. And so basically it will adapt to it by learning. So it will continually learn to adjust to the latest version of the environment, and we need an agent that is able to learn faster than the environment is changing in that case. So I've not really done experiments in that setting. At some point by mistake the environment was drifting and BDPI did well, but it's difficult because we don't really have pre-made solutions in reinforcement learning for those kinds of environments. Now, if the changes are faster, for instance, people are walking around, usually we consider that it's part of the stochasticity of the environment. So the agent will not really think about people are walking. The agent will more say that this distance sensor, for instance, has some nose to it. Sometimes it's closer, sometimes it's further. The agent doesn't really know that it's because of a person. You see that it cannot count on that sensor too much. And that's something where BTPI is relatively robust. So it cannot really reason about the fact that it's a person and then, for instance, imitate that person, but it can then still learn even though there are perturbations around the wheelchair. So it was a little bit shown on, I will just see, the fact that BTPI works well on this environment that has high stochasticity, so it's far from people in that environment, but it's still like the same theoretical concept of like random stuff is happening, and so the learning curve on frozen lake is good. So we see that the curve itself is moving quite a bit, but that's also due to the stochasticity. And also there has been an experiment that was done with BTPI on the wheelchair at a conference in Brussels here that was called the BNIG, for the Benelux Conference on Artificial Intelligence. And the idea was to have the wheelchair learn to basically avoid people in a room full of people. So it was the main hall where people were getting their coffee and things like that. And basically the wheelchair was able to learn that task. The task actually, it was not learning to avoid people, it was learning to move as fast as possible while avoiding obstacles. And basically what happened is that the wheelchair sort of discovered that feet were an indication of a negative reward because people are curious. So when they see a moving wheelchair, they get closer because they want to have a close look. And so that means that now that person who was far away is now close to the wheelchair because they're curious, and so the wheelchair gets punished. And so what I observed is that that wheelchair became extremely shy. So it was always running away from people and just doing little circles in areas where no one was seeing it. It was very funny to see that you can evolve like shyness by just punishing the wheelchair when people come close to it.
Maybe do your title page, that looks...
Oké, we zijn terug. Ik denk dat de rest ons vlug gaat vervoegen. Ja, ik zie dat iedereen terug is. Okay, I should continue in English. I forgot, sorry. So we are back. We have the deliberation. And now the secretary of the commission will do the proclamation. And that will be followed by a short speech of the supervisor of the NIE. So now I give the word to Professor Elisa Gonzalez Bosch, who will do the proclamation.
Okay, so Denise, this is a Flemish university, so the proclamation will be in Dutch. Unfortunately for you, it's not going to be done with a native speaker, so maybe you can also understand it. Zo, aangezien de heer Dennis Stekelmacher in het bezit van het diploma Master in Computerwetenschappen uitgereikt door de Universiteit Libre de Bruxelles in 2015 en oorspronkelijk proefschrift heeft ingediend getiteld Modern Free Reinforcement Learning for the Real World, aangezien het proefschrift door de examinandus in een openbare zitting werd verdedigd op 6 november 2020 aan de Vrije Universiteit Brussel, aangezien alle decretale en reglementaire voorschriften werden nageleefd, verklaren wij, voorzitter, secretaris en leden van de doctoraatstudie, aangesteld door de faculteit Wetenschappen en Bio-ingenieurswetenschappen van de Vrije Universiteit Brussel, dat de heer Dennis Stekelmacher de graad verworven heeft van doctor in de wetenschappen.
Proficiat, congratulations.
Thank you.
So, and now I give the word to the supervisor.
Yes, I will say a few words for Denis. So I must say, Denis, I think you have always been a bit a special PhD student in the sense that I will try to explain. So everybody is a bit special, but everybody's special in a different way. I think you were, let's say, frightening me a bit in the beginning. Yes, in the sense that when you were proposing your PhD topic, I was thinking, oh no, this is not feasible. You did your master thesis mainly with Peter. Peter Franks was then still in the lab. So he was like convincing me, yeah, but Denis can handle this. But while I was saying to Peter, no, we should downscale this proposal a bit because this is not possible. And then when you were like asking me, but it would be nice to have a robot, for example, a wheelchair, and can we send an email to InvaCare and maybe, can you help me to phrase that email? And I think Leander at the end was the one who sent it. I was thinking, oh no, if you now will start also to involve this robot, this wheelchair, and have to hack all these things to actually get something to work, I was, let's say a bit frightened that this would never work. But you have all surprises from that perspective, I would say, because not a lot of people who do reinforcement learning actually bring the algorithms to the real world. Okay, there's still interesting things to do. There's still challenges, but I'm happy that you want to stay in the lab. You want to continue tackling these challenges, and we're really looking forward to your next surprises, I would say. So very well done. I think we're all very proud of what you have shown today, and we can only congratulate you with this.
Thank you very much. I'm very pleased to hear. A little bit surprised that you were so afraid, but don't forget for the wheelchair that, well, I've been helped by Hélène, and that yes, it took a year to reverse engineer that joystick. So it was we tried interacting with the CAN bus in the wheelchair. It was extremely complicated. Yeah.
Thank you for your wise words, supervisor. Now I give the word to Denis. Usually we continue the evening with a reception, but these days things are a bit different. So I give the word to Denis to conclude this defense.
Well, thank you very much, and also thank you very much to all the people who have followed on YouTube. I see many congratulations. The problem is that I cannot type by not looking at the camera, and so this is why I have not personally thanked everyone. So I'm not forgetting anyone. there is indeed that question of the reception, and so currently we cannot do anything, but there is a sort of virtual ticket for a reception that everyone will keep for as long as needed. So we hope to be able to do it for my birthday in February. But given the oscillatory behavior that we currently see in COVID, it may be, well, I don't know which birthday it will be. I don't know if I will maybe be retired, I don't know.
Let's hope not.
Yes.
I think we will need to rely on some other ongoing research in the lab to control this COVID epidemic, right?
Okay, then I think we can conclude. I don't know if there's something still organized on the YouTube channel. And for us, the thesis committee members, I want to thank you for your contributions. And I wish you a good evening and a very good weekend.
Yeah. And by the way, I invite everyone to read the thanks in the thesis, because, for instance, like, I'm very grateful for everyone in the lab who has helped me, because all those things and the wheelchair, like, it was not possible without technical help, but also like psychological help from other people in the lab. And so it's too long to now mention everything, so it's available publicly. Don't hesitate to look at it. And even my other friends, non-lab friends who have followed me here in the lab, I've seen that they're doing things behind my back. They're also thanked in the manuscript, because, well, a person is always built on a collection of other people.
Okay.
It's a nice conclusion.
For your concluding words, and good evening to everyone, and all the best in these COVID times.
Yeah, thank you.
Good evening and congratulations again.
Yeah,
thank you.
Congratulations, yeah. And
Bye.
forget about your birthday.
Sorry, no, I did not hear
We
you.
will not forget about your birthday when we can have finally that drink.
Yes, indeed.
Okay, bye.
Bye. Have a nice weekend to everyone.